Welcome to Tool Steel Procedures and Metallurgy. This is Metallurgical Program P9, and this is representative of gas tungsten arc welding procedures. What we're going to cover over the next little while represents exactly what we need to know to perform tool steel operations, tool steel welding operations, and we're going to go through some of the finer details of what we need to do to both prepare and to do things after the weld has gone into place and understand what we need to do. So, metallurgical and chemical. We need to do a little bit of chemistry here. We need to know a little bit about what's going on with the tool steels. So whenever I'm doing a tool steel program, I always utilize this particular slide because I want to explain a couple things about welding. And by the way, this is going to take us much further than just tool steel welding or any other type of welding. It is all welding. So when I look at the first section here, I see a solid. A solid represents a piece of material that's solid. This could be water that's frozen. And I like to use the term of water. When I'm teaching metallurgical programs, I like to spend about the first hour or more talking about how I can change water by adding things to it when I can make it freeze. So let's look at the solid for a second. When something is in a solid, the atoms are arranged. The atoms and the molecules are arranged in such a way to give us a certain amount of strength. And they arrange themselves based on what they are. Now notice when I take something, and let's just supposing this is a frozen ice cube. But if I take that frozen ice cube and I take it into a liquid, the liquid actually, look at this, it's got atoms that are floating around. They're in the air. So what they're trying to tell us by this is when something is in liquid form and held in a liquid form, something gets depleted, something gets burned off, something turns into fume. And we know that there are fumes that come off of these welding processes, right? It's no secret. But here's what we need to know is the longer we keep a piece of material in a liquid form, the more the metallurgy changes forever. And that is certain aspects of the metallurgy end up boiling off, giving us a property that's different than the property, maybe even the property we're looking for. And that is, a lot of it has to do with hardness, especially when it comes to tool steels. So think about water for a minute, and we have our ice cube, and now it's starting to boil. So now even liquid just sitting in a glass is going to start to evaporate. But when we have a pile of heat added to it, we actually force that evaporation to happen. And there is no difference here between using water as a base or using iron as a base. And we only make steel by taking iron and dripping, dripping carbon into it to the point where it actually dissolves. Remember that carbon doesn't mix or sit in iron. It dissolves just like salt dissolves in water. If I take salt, I can keep adding it to water, and you can't tell there's any salt in it. All of a sudden, the salt will go in and the water will become cloudy. That means that the water's saturated. It can no longer handle all the salt that's coming to dissolve. Carbon dissolves in the steel to give us a certain hardness all the way through. The last piece of this is plasma. Plasma is just ionized gas. Without plasma, none of us are welding. Plasma is a controlled lightning strike. That's all it is. And we're going to give it the special gas and a special current and a special voltage, all the things we need to give us the heat we need to get our welding processes done. So here we are with our little stew here. We've got carbon and sulfur and phosphorus and manganese and all the things we need to make steel. And these are the basics, right? Sulfur and phosphorus give us the opportunity to be able to be machinable. If we didn't do these, we couldn't run a drill through them or anything like that. They help with malleability. Manganese stops something called hot shortness. If you didn't have manganese in steel, steel would be red hot and brittle as glass. And it's a crazy thing to see a piece of material get red hot and you hit it with a hammer and it breaks like a piece of glass, because manganese stops this hot and shortness condition. So remember that its carbon will dissolve into the molten iron because iron is a dictator solution. A little bit of grade 9 science for you there. Now, this is important for TIG welders everywhere to know. But we have a responsibility as TIG welders to try to control the temperature of our components. Aluminum, coppers, and all these things, they all have melting points. They all have the point where their material just can't hold up any longer, and it will start to melt. But note this. Look at these boiling points. Material not only has a melting point, but it has a boiling point, and all these boiling points are down inside of the temperature that the plasma arc carries. So you could take any of these materials and not only melt them, if you are not careful, if you don't have the skill set, if you are too excited about using that pedal and getting everything too hot, you can not only melt it, you can boil it. And if you boil an alloy, if you boil any of these tool steels, that area is going to be changed forever. You won't be able to do anything with it. Now here's our typical periodic table. I like to throw this up now and then and talk about what we're doing. So iron here, and then chrome. Now we're starting to talk about tool steel. As soon as I see chrome and iron, now I'm talking about chrome steel. Chrome is one of our hardening elements. Now nickel works as a really good joining element. So if we have a lot of nickel in a filler material, it's very good at joining tool steels. Now remember this about nickel. Nickel will not harden. 300 series stainless, this type of stainless you see in your sink, the type of stainless that's nice and shiny for the really good barbecues. All these stainlesses, they cannot be hardened. The nickel content won't allow it to happen. But because of that property, one of the things it does well, that it'll weld high carbon materials, and the weld itself won't be contaminated by all the extra carbon or chrome. It doesn't care. The nickel keeps everything soft. Then we of course we got our carbon and our molybdenum. Now we're getting into the materials that we or the elements that give the steel its hardness and its toughness. Vanadium is one of the toughest. You get a material that's looking at, when you're digging into vanadium, you're talking about materials that are probably going to be in the Rockwell 60 range. Now these are pretty tough tool steels. Vanadium enriched stuff is usually up in the D2 stuff. And titanium is commonly found in tool steels and in stainlesses because titanium loves to mop up impurities. And it does this very well. Silicates and titanium do a lot for us, especially when it comes to stainless. Phosphorus, we already talked about that. Silicon. Let's talk for a moment about this W here, which happens to be tungsten itself. We can actually have tungsten in tool steels. Tungsten, remember, not tungsten carbide. We're not having tool steel parts here, but tungsten itself is not that hard. It's very tough. Tungsten steel is very tough, and because there's no carbon in it, it's super tough. Anything we want to make with tungsten is pretty tough stuff. High impact. So let's play around here for a minute. Look at where vanadium can take you for carbides. I'm always shocked by this. So chromium carbides and how we can influence our puddle has to do with these particular alloys. And this is more than just wear resistance, even though wear resistance is shown. We're talking about wear resistance, impact resistance. If I want more impact, right, I can form some tungsten carbides and I can get things really tough. But tungsten carbides need to form. Remember that the tungsten we're using in our welding process as our electrode is not tungsten carbide. This is the carbon phase diagram. I'm not going to spend a lot of time on it, and this is a completely separate program to do this. But this particular material shows a couple of things, and what I want to do is I want to just talk for a minute about how heat affects things. So there's a magic place right in about here. And this particular place is where there's 0.83, this is 0.8, but 0.83% carbon and about 720 Celsius, where when you heat up a piece of steel, depending on its carbon content, it tells you what the state of the material is. Now, we want to shift material between these to try to get a material harder or softer through our welding process. Now, this is the typical carbon phase diagram. You need to spend a little bit of time in here to make sure we get more austenitic material into our welding process. This is a zone we're looking for. And some of this, we start to get to an embrittlement with cementite. But we want to get into these zones to make sure that when we quench these materials, we end up with the hardness that we're looking for. So we'll talk a little bit more going forward, and I will refer to the carbon phase diagram so you can find out more about its eutectic point. And that's the thing that you find here right now. There's a name for this, and I didn't want to get into it too much, but this is known as the eutectic point right there. And if you get it above that, remember, it'll change all of its properties. When material's sitting there and it's above a certain temperature, depending on its carbon content, as soon as you rise the temperature, the properties change forever. I'll go on. I've got a few more slides to show you that will define this a little further going forward. Here's a nice little table that I always like that I'd like to reproduce one day, but it says it's from an old book that shows the carbon and chrome and what classification of materials. So where our chrome and our carbon content comes into play, when it comes into like 1% or 2% or getting into the percentages of chrome, right? SAE steels, which is our Society of Automotive Engineers, are basic steels when it comes to that. But look at our 500 series stainless grades and everything, where the chrome content is. And then as chrome and carbon rise together, which is out here somewhere, now we're in the hard facing and the wear resistant materials. So it requires chrome and carbon to get us where we need to be. These are the reasons why we have to be very careful about what we select for filler material. Base metal and property and base weld metal and base metal properties. I want to go into changing the tool steel a little bit. So let's talk a little bit about grain structure for a minute, because we modify grain structure when we actually TIG weld. When we modify the grain structure, we make the grain structure in such a way that it doesn't really have the strength that it did. So let's talk about a component that we need. Here's one right here where it shows the finished component. This is what we want to make. Now, what we want to do is we want to grab this finished component, and every machinist out there says, give me 5 minutes. And he puts this in the lathe, and he puts a grip on it, and he takes it, and he machines these pieces off and ends up with a part. Here's the problem. This material is not as strong as it could be, because we've taken a lot of time to actually take grain structure out of this. The grain structure has been cut. It ends. It's like drilling a hole in a tree and interrupting the grain. It's never going to have the strength that we want it to have. So if we're demanding of it to be strong, it's probably not going to happen. If there's any impact, for example, going this way, this is probably going to be very weak. As opposed to a piece of material that comes out and gets forged, and that is, it's above its critical temperature, it's above its eutectic point from the carbon phase diagram, and we're going to push it around and forge it. We're using drop hammers and all kinds of different things. We're going to push it around while it's red hot. So when it cools off, we end up with a grain structure that helps us in strength. That's the idea. That's why you go out with all your wrenches and they all say drop forged and that on it. That means the grain structures are even throughout based on the shape of it. It wasn't machined out afterward. Now we can heat treat things in an oven. This was a very good oven. It was capable of 2,000 degrees. Now, when we figure out what we have to do for the schedule for handling this piece of material, sometimes it's going to mean putting things in the oven beforehand. Sometimes it's going to be post-heating, and that is giving it a little bit of extra heat afterward. I always used to keep one oven running in a tool steel shop at about 550 degrees. And that was going to be a pretty handy oven. And if it's a small enough part, I put a piece of heavy plate, like 1-inch thick plate underneath it, and preheat everything together. If I'm preheating everything together, then when I pull it out, it's not going to go cold fast sitting on a cool bench. So I always put it on something that kind of helps it to support the heat that's in it so I can do my weld process. So I've had a lot of tools that sit in about 400 or 500 degrees for a long time. It hasn't seemed to affect the strength or the operation of the tool, the clamp, or whatever I've happened to use for a long time. But but that's a really good temperature for welding materials, as you'll find, that's already hardened. If the material's already hardened, you can actually weld it and leave it in its hardened state. We don't have to wipe out its properties. You're going to do a good enough job at that, welding it. But we do have to preheat to get rid of the thermal shock capability. Thermal shock comes when you've got a cold piece of tool steel that's just looking for a problem, and you come along and put a 10,000 degree arc on one side of it. It will snap somewhere. It'll crack internally, just at the differential of temperature. A little bit of heat in it messes with the tool steel a little bit. Makes the tool steel think it's a little bit not as soft, not as hard as it was. It makes it think it's a little bit softer. It gives you a little bit more room to play with it. Now we can heat it a bunch of different ways. You don't have to heat everything using an oven, even though every good shop has one. But you could also use local torch. Now, if you use a local torch, when I come to your plant, if I come to your plant, if you use a local torch, what we'll do is we'll set up some exercises on how to preheat, and I'll do demonstrations using different things, using maybe a flare gun, using temperature sticks. I'm a huge fan of temperature sticks, but you have to use them properly for them to work. You could use oxy-fuel flame, you could use propane flame. These are the flames of choice because it's referred to as soft heat. When you use soft heat, you could actually go in, put the flame on it, and it doesn't concentrate heat. It's not going to turn it red hot in that spot because it's a much larger flame. Oxy-fuel flames, like off of torches like this, will melt through things and flash. So let's talk about heat here for a moment. And I'm going to talk for a second just about that carbon phase diagram again. When material is sitting there in front of you, remember that it has potential. It's sitting in front of you, it has potential for hardness. Now, I'm going to show you how we go ahead and get that hardness out of it and maximize it. So we have a material in front of us that has an existing structure of properties. And it's carbon steel, but it may have something in it. It may have chrome, it may have vanadium, it may have tungsten carbides, it may have all these different things that can give tool steel their properties. Now what we do is we apply heat to those. And if we apply heat to that material, they'll hit a certain place based on the temperature and the carbon content in the carbon phase diagram. We will wipe out all of its properties. This is important. This is a really important moment. When you get these materials to a certain place in temperature, even though you can just heat them up a little bit and weld them with a tool steel, if you get too carried away with your heat, they will lose their properties. They will no longer be hardened. If it's your intention to make these hardened, if it's your intention to keep these hardened through your process so you don't have to requench anything, then you have to be careful how much heat you put into it because you will wipe those properties out. Now, supposing we took this material, we put it in the oven, or we grabbed it or heated it with a propane torch, we applied our heat, and now we've got it up over its critical temperature, over its eutectic point, where now it has no properties, and it's waiting for properties. So here's what happens. We can change what happens if we cool this material very quickly and quench it. If we make it as fast as we possibly can, and if you want to cool something as fast as you can, you do it with salt water. Salt water, also known as brine, will actually, it makes it difficult for it to boil. So it hardens and it makes it difficult to boil, therefore it cools, and it hardens the material the best it possibly can. Now then we slow it down a little bit and we don't take it, we end up toughening material. And if we normalize, we're actually starting to take it now, and then we slow it right down to its lowest, and we're annealing it. So depending, we can start off with existing properties when they're wiped out. It's up to us. So it's up to us how to find the potential for this material to give us that hardness. So the fastest end up giving us the hardest result, and the slowest end up giving us the most annealed result. And the annealed is the softest possible condition for this material based on its metallurgy. Now, I talked a little bit already about quenching, and if you ever watch Forge and Fire, you understand this very well, that once material gets to that temperature, we also call it kindling temperature, eutectic point. it gets to a point where it has no properties. Now there's different ways to actually get these to quench. I already talked about brine. Salt water is the fastest method, and then regular water for unalloyed tool steels, and then oil. And this would be O1. O1 would be a perfect example of using oil for a low alloy tool steel. And now when we get into the high alloy stuff, we got to be careful dropping anything in any form of liquid. It'll shatter. I've seen them jump right out of a quenching pot just because somebody took a piece of D2 and had it up hot enough, and it actually shattered inside the liquid and put the liquid all over everybody. And it was oil. And everybody, there was about 4 people in the area, and everybody had oil on them from this thing. Plus, it caught fire quick. The oil will actually catch things on fire. So when it popped out and all the pieces popped out, they all had oil on them, and they all were on fire. So it was about 4 or 5 chunks of burning stuff all over the place, and the guy close to it had a bunch of oil all over him, where it just kind of went in and popped right back out again. Now, of course, then there's forced air and static air. Forced air, you put it on like a downdraft table, and it'll be fine. Static air, like you find this often for D2, you just let it sit on the table. Don't blow on it. Don't do anything. It's going to be hard. It's going to be hard enough just sitting the way it is. Tempering is something we do to tool steels afterward, or anything that's higher in carbon content. Now, I like this little cold chisel picture because it's so simple, but it breeds the truth. We have a chisel point that has been dressed, and we've taken that and we've done what we normally do. We heat up this area and we quench it. So we're going to put it inside of oil. We're going to drop it in oil after we get it to its eutectic point. We're going to put it in oil, and we're going to do figure eights with it. We're going to do figure eights. We're going to get it cooled off. And then it's going to turn all kinds of colors. It's going to turn purple, and I just put it in and pull it out, put it in, do a few figure eights, pull it out, and I keep watching it. Now, what I want to do is I want it to be in its hardest state, but I also want to make sure we get an opportunity to temper it. The tempering process reduces, it takes the stresses out of it, because there's the hardening process and quenching process causes a lot of stress inside these higher carbon pieces of material. And if you don't temper these, and the old term, if there's any old guys in the room or old people in the room, the term used to be drawing back from hard. And what it means is we have to take a little bit of the hardness out of it and temper it slightly to make sure that it's not ready to shatter as soon as we touch anything. This is most of the reason. If you don't temper, this is for this reason, you'll end up something breaking very easily, even though your weld was perfect. It might just be sitting there under stress and it needs to be relieved. And there's ways of doing that. If you have that oven, for example, that's sitting there at about 400 or 500 degrees, that's about where I want it to be. And what I do is I shine it up. I take it over to a sandblasting booth, or I take it to a buffing disc, and I just shine it up and get nice shiny steel after I've gone cold. And then I put it back in the oven, and I leave it in the oven until it turns straw, a little bit of like a yellowish tint to it, and then it'll be fine. Flame hardening is another way of doing it, where you simply apply a flame to the surface very quickly and then quench it right afterward. This is pretty tricky. If anybody wants a demonstration of flame hardening, you should let me know, but you need to have a certain amount of carbon or you can't get it to happen. And just while we're here and talking about it, it's important to note that if you don't have the correct amount of carbon content, you're not going to get hardening to happen. Carbon is the basics, and then all the other things add to it. Carbon, and you add chrome to it, wow, you're really getting hard now. Drop in a little bit of tungsten, tungsten carbide, drop in a little bit of vanadium. Now it gets harder and harder. Now, you can get the carbon content in a material just perfect to the point where it's pretty tough. But if you heat it up to its eutectic point quickly and then quench it in oil or quench it in water, you can make it so that the surface is hardened, but not underneath. Perfect example of this, lathe beds. Lathe beds actually have a little flame that travels along. and it's it's got flame on it, usually acetylene, and it turns the material red hot, and then right behind the red hot material is a stream of water that's just pouring out, cooling everything off while it's while it's above its eutectic point, to make sure that the surface of the material is hardened, but underneath it is still ductile and able to take a whole bunch of abuse. The objective here is to make sure that that surface is wear hard. That's what they're trying to do this for. So they would take it from there and it would go straight for grinding to make sure we had everything we needed to do for the properties. Here's a good example. I want to talk about a term here known as dilution, because this is diluted. And when we do our TIG welding, when we do our tool steel welding, there's always plain carbon. No, I shouldn't say there's always, but there's plain carbon steel possibly underneath it, or a tool steel of some kind. And we have to put layers on. Now, in this particular case, it's just carbon steel. And we've taken a tool steel and we've put a layer over top of it. Now, dilution is the question here. Dilution is how much hardness do I have in this layer, because the carbon steel has infected, if you will, this first layer. Now, this dilution that we're dealing with will actually take away some of the hardness. But if you put another layer on it, if we get up here and put another layer on it, the Rockwell hardness gets quite a bit more. Point being, the more layers of hard material you put on, the more of an effect you're going to have on the hardness, to the point where you might get a little bit of a crack. So you got to be careful how many layers. You have to know your filler metal is one of the other points. You have to know the filler metal you use and what you've been using to achieve a certain thing. Some materials you just cannot put 3 layers on it or it will start to crack. And there are tool steels out there, tool steel filler materials, that are made to crack. We have lots of them, and they use a lot of these even in places where the drilling heads and all kinds of things, that where the tool steel surface will crack, and that's normal. It's just that hard and that wear hard that we have to consider for it. A quick word on establishing temperature. We've got a bunch of different ways. Now, our tool steel, during our tool steel program, I'll demonstrate the tempo stick. This is my favorite method of doing it, but it requires a little bit of thought and a little bit of planning, because when you get to a certain temperature, these sticks won't work anymore. You have to recognize how they work. Every good tool steel welder has 2 temp sticks with them. 2. One that represents the highest temperature they have, and one that represents the lowest temperature that they are going to achieve. These things are represented. The highest temperature represents inner pass temperature. The lowest represents minimum preheat. Now, temperatures can be assessed with infrared. I didn't bring my FLIR. I didn't add the FLIR to this, but I will actually be doing a demonstration. I'll bring my FLIR camera for any type of practical training that's done, and we can do a little bit of a survey of your components. Now, I threw this little table in here to remember something, because I already said straw color. I was talking about color. I shine up that chisel and I bring it up to temperature using straw, using straw as the color for my goal. Now, if I get this right, I'll get about 400 degrees, and I will. Now, this is important. Now, I'm going to lose a little bit of Rockwell. I might lose 2 or 3, maybe up to 5 Rockwell by doing this. But the longevity and the lifespan of this joint just went up exponentially. So we need to consider for that. We need to make sure that we do a little bit of drawing back from hard, right? Old term again, or tempering, or some materials want a double drawback from hard. You might look at your procedure, and your procedures will tell you everything. Every company, Eutectic, Eureka, all these different companies that make tool steels all have procedures all written out in books. We're going to explore a couple of them very soon. I like this picture. This is actually a die off a brake press. And as we cut it, the edges, the heat started to come in and it showed color. And all these colors, as we've seen back here, all these colors actually mean something. So these colors freeze time for us as welders. These colors freeze time and show us how hot the temperatures got in the steel while it was being exposed to air. This was when they just threw it in a chop saw and started bringing it down. And this is where we ended up. And you could actually see the different colors and what they are. So I rely on this quite a bit to know about welding. When I'm looking at stuff on the shop floor that's being welded, the cold rolled materials that we're doing to make our automotive parts, I like to look at the other side and try to read a little bit about the heat inputs based on what these what are called temper lines, based on what these temper lines do and look like. Tool steel techniques. We've talked a little bit about this already, about making sure you keep the tool steel rod inside of this area where there's gas. If the tool steel rod remains inside there, it's already protected. The weld remains protected. Everything's good while the plasma ends up melting our component. And as long as we keep this inside protected, everything should be good. The tungsten itself, of course, is non-consumable, but it needs to be watched. And if you ever touch the filler material, even accidentally, to the tungsten, immediately stop and immediately change it. It will actually start causing a lot of problems to the metallurgy in your material because you've added this material to it, and it'll actually end up sticking there. So you need to redress and take it back. Big deal. Quick word here for safety. Never, ever sharpen both ends of a tungsten for a bunch of reasons. First reason, when you're sharpening it, you shouldn't be holding on to a sharp end. There shouldn't be two sharp ends. Second reason, how do you know what kind of tungsten it is now? You've taken the little band of color off of it, and now it turns into a big problem. We don't know what it is. It should just get tossed in the trash. Now, a quick word on hard facing, and I've talked about this a little bit, but let's define it. Sometimes when I got to build something up too far, I might put a layer of stainless steel underneath it. 309L is common. Nickel, or what they call Inconel, 625, it's almost all nickel, and lay down beds underneath it. A bed of nickel is ductile, and we can add hardened filler material to it. What happens if you try to add hardened filler material to plain carbon, we start to get an accumulation of carbon from the base metal down here. And the accumulation of carbon just continues to grow until we end up with voids or cracks, I should say, from areas that end up too hard. So sometimes when we want to bring it up a little bit too much, a little bit more than we should, we end up wanting to put a layer of underlay, and this is underlay or base metal, or there's all kinds of words to describe this, but this buildup is representative of a softer type of material. Heat affected zones and the conditions. Remember that when you put a big weld in compared to a small weld, you start to anneal the area around it. We already talked about annealing being the slow heat release. So if I put a big weld in, it takes a long time to cool off. These larger welds will actually start infecting, if you will, more heat affected zone than a small one will. This might be a little too small, but there might be a happy medium here where we're getting some heat affected zone annealing, right? But we're getting the material put on. Some of the bigger welds don't last. Bigger is not better when it comes to this. And bigger actually creates more heat in the job. We need to understand interpass temperature too. How hot is this going to get? How hot can it get? Right? What is its eutectoid point based on the information we have? This is all us knowing what your base metal actually is. And then it's pretty simple to figure out what all these other temperatures are. Sometimes you get something broken. There's something referred to as a buttering pass, where we'll put a little bit of nickel on two pieces and bring them together, and then we bridge it with a little bit of with nickel electrode. We make sure this is on here nice and safe, and then we go about this and we put on these buttering passes. This is a repair procedure if you get a die that's broken and we got to get it working. The best thing is to actually make sure that we replace the part. Sometimes if we're stuck and we got to put on a buttering pass, it's a very simple thing to do, and it makes it very nice to weld afterward. But you do have to respect your interpass temperature, because these layers, if you get all this too hot, these layers will pull right off and start to curl towards you. If you get any cracking, it's a bad thing. Of course it is. But cracking, is representative of stopping. If you're starting to see cracking during your welding process, you've got a bunch of things. And if you get a crack on the very first weld you put in, just stop. Something has happened. You might have excessive preheat in it, or maybe it's got become too hot, or it was already too hot. The joint is mechanically frozen, meaning that it won't move at all. So it's the weld, when it shrinks, it's pulling itself apart. This is usually indicative of having it all too hot, and when it cools off, it starts to pull apart when it shrinks. You could also have the wrong material here. It could be the wrong material, it could be the wrong base metal. Never start messing around thinking if I just keep going, I just keep trying it, it'll start to work. When you see this happening, it's highly likely that your base metal is contaminating your weld metal. We need to look at it all again. We need to look at what's going on if you ended up with a crack like this. Underbead cracking is most likely insufficient preheating. Now there's some incompatibility issues, but if you just try to throw heat on top of a material that's extra hard, it will gravitate, all the hardness will gravitate towards this hot zone where it's being quenched, and actually this will turn into a barrier of carbon and chromium oxides, and they'll form underneath the weld, and you could actually take a chisel and pop the weld right out. The other option is you could end up with these few cracks underneath the weld. Don't undercut on hard material. Undercutting is like putting a sign right here that says crack here. It's a little bit of a notch you'll find in the material as a result of your tungsten technique and manipulation. If you don't add enough filler material or you do something wrong, it's going to cause you a world of hurt, and this will crack like nothing. So you have to make sure under all circumstances, especially if there's any machining going on, that you don't have any undercut between these layers, because one little bit of a notch on this type of hard material means a crack later on. A few words about tool steel alloys. Alloyed materials is when you add certain things. You'll use here the term plain carbon steel. That means it's basically phosphorus, sulfur, iron, I should say, in phosphorus and sulfur and carbon. And all these things are melted into it, and these are referred to as plain carbon steels. I can make them tougher. I can get up to get 0.45. I can get 1045 material. That's very, very tough. It has a lot of carbon in it. And I could make a heck of a knife out of that, actually. We can get a really good, tough surface and still keep the back end of it, the trunk of the knife, a little bit annealed to keep it soft enough that we have impact resistance. So we can hit something hard with this knife and maintain the edge, but not shatter. All these materials here are all very special. This is what's referred to as alloy steel. If they have one or more of these elements, in respective amounts, they're referred to as an alloy steel. The nice part about alloy steel is we have enormous control over what we can do with them when it comes to heat and temperature. We can create gears, we can do all kinds of things and harden the surface, but keep the material in the middle soft and annealed so it's not brittle, but the outside wear hard. We can do all kinds of things. The downside of these materials is they're all reactive to heat. It's almost like a double-edged sword, because being reactive to heat, we have to make sure that we don't transform them when we weld, so we don't make the machinist very angry at us when we're over there trying to machine it and we got to take it to a grinder just because everything's so tough. Executing a tool steel procedure. We have a bunch of different types of tool steel. We've talked a little bit about some of them, and we haven't been specific to what the work is being done. But there's shock resistant and cold work. There's a couple of special purposes which get into the very hot stuff and the hardened tool steel. When we're doing special purpose stuff, would be a perfect example would be heat treating hot or doing hot copper. Copper does a number on steel. Believe it or not, it starts to wear it away really, really, really quickly. So when we're trying to cut anything of copper and it's hot, we get an exceptional amount of wear. When we're talking about H class, which is very common for boron steels and so forth, we're talking about the hot work process. And mold steels, these are pretty high, pretty normal. materials that get used daily. Cold work is common. I mean, most companies use O1, right, which actually falls into that series. And the A series is the A1, A2, and D2, of course, is very, very hard. That's where we're talking about extra copper or extra chrome, sorry, and extra chrome and extra carbon. So whatever they have to do. The shock resistant, you'll always find tungsten in shock resistant because it's tough. So I have in front of me the data sheet from a tool steel book. This particular one of them is from a company called Crucible. What I want to go through here is a procedure that's being used to do this. So this is for, let's look at this, American Iron and Steel Institute 01. So this is 01, which is an oil hardening. It requires quenching in oil to give us the hardness we need. We have our composition here. We can see all our stuff, right? We can see, oh, look, there's even 0.5% of tungsten in there. Things that we need to make it really tough. 01's a great material for punches and all kinds of things. As long as you're not trying to do a shear edge with it, it's a real good utility as far as I'm concerned, because you can get some good hardness out of it. What I want to talk about for a minute, what I want to examine, is the hardening process, where we're going to create a certain temperature here. Now, there's something inside this procedure that I want you to see, and every company should have something like this that you buy tool steel from. The critical temperature. The critical temperature represents 1370 degrees Fahrenheit. Now, that temperature's eutectic point. That's the point when you get it over that temperature, all the properties are wiped out. So let's look at what happens here to harden. So it tells you to preheat below the eutectic temperature, just below it, because once we get it to the eutectic temperature and everything's gone, you could have a problem, right? Because you don't want to leave it in its critical temperature, above its critical temperature for any length of time. So we're going to preheat. So what's going on inside the material is the same temperature. So we got 1250 degrees to 1350 degrees, just under its critical temperature. But then just before we do it, we're going to high heat. We're going to go 1450 to 1500. We're going to take it just over the critical temperature, and we're going to hold it there for 10 to 30 minutes, 10 being if it's a very small part, 30 minutes if it's a bigger part, and then we're going to quench in oil until it's hand warm. So you're just going to put it in this thing, and by the way, you're not going to just drop it in there. You're going to drop it in there, and you're going to do figure eights, and keep the temperature going until it finally goes to the point where you pull it out. If you pull it out, it's still smoking, put it right back in there. And keep it going until you can pull it out and touch it with your bare hand. And look what it says to do next, because it lays out. So now we got the critical temperature. Then we take it to the preheat. Then we do the high heat. Then we do the quench. Now we temper. Temper is also known, and we've talked about this already. It's drawing back from hard. The drawing back from hard process is to put it back into a temperature that's not going to affect the hardness very much, but bring it back up to temperature where residual stresses have been removed. Once residual stresses are removed, it becomes much more durable, right? You could actually use cryogenic treatments as well. You could freeze it the rest of the way to get complete hardness. You have to be very, very careful doing this, and you have to do it only under the instructions of the company that designed the alloy. You actually need to look at that data. And there's a few companies that make stuff that respond very well to cryo treatments. And cryo treatments, by the way, dipping it in liquid carbon dioxide, dipping it in liquid nitrogen, things like that. I've even seen them say you spray it with a CO2 fire extinguisher for 2 minutes. Things like that we'll find in the procedures. Now you got a difference when it comes to welding. You can weld annealed material, 01, and it tells you how to weld annealed material. We're going to preheat it to 400 to 600. Remember I said I'd have an oven in my shop at about 500 degrees and leave it there? Yeah, if I've got annealed material, I'm going to heat it up that high. But if I've got hardened material, just a little bit lower than that, I can maintain, as long as I don't go over 300 degrees or so. If I care about how long I leave it in there to have that temperature, I can go ahead and throw it in that just long enough to get me up to about 300 degrees, and I can do my welding on it. And then I retemper twice, draw back from hard or double draw back from hard until I take it to the original tempering temperature. And then I just let it cool on the bench. I cool everything on a piece of wood that comes out of something like that because I don't want the temperature of the bench to affect one side more than the other, and it will. So here's a good example of what a good welding procedure looks like, right? These last 2 pages, because they define all the things I've been talking about understanding your procedure. Now, you may have a special procedure that requires doing something a little bit differently, and that's fine. And you can always contact me if you wanted to get into some of these, if you get into some really tough materials with D2s and you're getting cracking and all that. But we can figure everything out. A few words about crack detection. Visible dye penetrant is very common. You get a 3-part visible dye penetrant where you spray a cleaner on the surface and then you put a red dye on it. The red dye soaks into all the cracks. You wipe it off and you spray another can of stuff on it, and it actually starts to draw. If there's a crack, it'll start to draw it out, and you can actually see where the crack is. This crack, this red section, is known as an indication. An indication is where all the dye is being drawn out of the crack and showing us where the crack is. It's commonly done when you're dressing the crack, trying to figure out where the crack begins or ends. So it lays down and gets inside these cracks, the dye. And the dye is also known as a penetrant. And the penetrant will actually go in, and it's not unlike WD-40. It will actually go inside and find all these little cracks and crevices. It'll eat through it. It'll dilute any types of moisture or oil to get down where it needs to go. And this is why, when it's given the opportunity to fill these completely, that's why if it's a deep crack, I get a huge indication. There's a whole bunch of red out here with my aluminum chlorhydrate. It's actually not too far from the stuff you spray on afterward is a red powder, and it's not too different from underarm deodorant. It has aluminum chlorhydrate in it, and it sucks the liquid out of these cavities to tell us where the cracks are. I'll do this sometimes to start the job. I'll do it when I'm done dressing it to find out if that's what I need to do, to find out if I've got everything I need to get out of there in order to get me to the bottom. Sometimes you just can't. But if you can't, now you're using softer materials at the bottom of it, and you work your way up till you get closer to the top. You keep your material nice and soft and ductile. Now you're up getting close to your finishing passes, your hard facing passes, and everything's nice and even, and you can continue. So that's the end of the metallurgy, just specific to tool steels. I'll be going over this a little bit with everybody if you go through the practical with me, if you have a practical session, and we can go through the details of how to prepare things and look at your job specifically to find out if there's anything different you might need. Have a great day, and always remember to work safe. Bye-bye now.